Quadrilateral interior angles sum theorem. Angle measures of polygons. Earlier in this presentation, various properties of triangles have been discussed. What are some of these properties? If you have the ability to discuss this with a classmate, pause the video and do so now. Or pause the video and make a list of some of these properties that you recall. So what are some of these properties? Well, some of the answers could have been any of the following. Side length classification, such as equilateral, isosceles, or scalene triangles. Angle classifications, such as equiangular, acute, right, or obtuse triangles. Or the triangle sum theorem, where all the angles in a triangle add up to 180 degrees. Let us revisit the triangle sum theorem. The theorem states that the sum of the measures of the angles of a triangle is exactly 180 degrees. So given this triangle ABC, in equation form, the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees. Diagonals of a polygon. A diagonal of a convex polygon is any segment that joins two non-adjacent vertices. Let's talk about some of the big words in here and break them down. First of all, talk about the word convex. Convex means that every point inside of a polygon can be connected without going outside of that polygon. The opposite of that would be concave, and I'll demonstrate what a concave polygon looks like. Here's an example of a concave polygon. If I want to connect 2 points within the polygon, say I have a point here and a point here, I would have to go outside of the polygon to connect those 2 points. So that's a concave polygon. A convex polygon is a polygon constructed in such a way that no matter what 2 points I connect, that line segment will always be within the polygon. The other word I want to talk about is adjacent. Adjacent vertices. Adjacent vertices are vertices that are next to each other. So like C and B are adjacent. They're already connected with a line segment. Non-adjacent vertices would be vertices like C and A. Okay, they're not adjacent, so there's a line segment connecting them. That line segment is referred to as a diagonal. So if we have a diagonal going from A to C, starting up here at A, going down to C, we also have a diagonal going from B to D, starting at B, going up to D. We have a diagonal going from C to A, and a diagonal going from D to B. And you may notice that there's a repeat, okay? A and C is the same as C to A. B and D is the same as D to B. Counting the number of diagonals leaving each vertex results in each diagonal being counted twice. A convex quadrilateral has 2 diagonals, not 4. Diagonals and dissection. Every convex polygon with 4 or more sides can be dissected or split into contiguous or touching triangles by the diagonals drawn from a single vertex. So if I draw one diagonal from a single vertex, I have created 2 contiguous triangular regions. I'll highlight them so they're easier to spot. If I draw a diagonal coming up from this way, I have a triangular region here, and I have another triangular region which is contiguous or touching down here. There are only 2 ways to dissect a quadrilateral into 2 contiguous triangular regions. This is one way, or I can run my diagonal running up in this direction, and I can form 2 contiguous regions as you see here in the diagram. Let's put these 2 ideas together. The sum of the measures of the angles of a triangle is exactly 180 degrees. Every convex polygon with 4 or more sides can be dissected into contiguous or touching triangles by the diagonals drawn from a single vertex. Which leads us to this question. What is the sum of the interior angles of the quadrilateral PQRS? The dissection into two triangles allows us to turn this into a problem we know how to solve. Because the sum of angles A plus B plus C is equal to 180. I'll write that in. And the sum of angles D plus F plus G is also equal to 180 by the triangle sum theorem. So the sum of the interior angles of PQRS is 180 plus 180, or 360. By adding up all of the angles from the first triangle and the second triangle, we attain that the sum of the quadrilateral is 360 degrees. The quadrilateral interior angles sum theorem. The theorem states that the sum of the measures of the angles of a quadrilateral is exactly 360 degrees. In other words, for any quadrilateral, if you add up the four angles, the sum will always be 360 degrees with no exception. Algebraically, in the terms of a formula, we can write the quadrilateral interior angle sum theorem as this way: the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D is equal to 360 degrees. Now that we have proven that the sum of the angles of a quadrilateral is 360 degrees, let's use this theorem to find missing angles of a quadrilateral. In this diagram below, we are given three angles. Angle D is missing. So what is the measure of angle D in the diagram below? We are given that this is 120 degrees. This symbol here means that this angle is 90 degrees. That's the right angle symbol. And we're also told that angle C is equal to 60 degrees. So here we have angle A is 120, angle B is 90, angle C is 60. Plus whatever the measure of angle D is, has to total 360 degrees. If I add 120 plus 90 plus 60, that gives us 270 degrees, plus the measure of angle D is still equal to 360. Subtracting 270 from 360 leaves us with 90 degrees. So the measure of angle D is 90 degrees. So let's use the quadrilateral interior angle sum theorem to find the measure of angle H. So what is the measure of angle H in the diagram below, given three of the angles, but not knowing what this angle is here? Given that angle E is 45 degrees, angle F is 90 degrees, and angle G is 120 degrees, we take these three angles plus the missing measure of angle H, and we know that it's going to have to equal 360 degrees by the quadrilateral interior angle sum theorem. Next, we combine 45 plus 90 plus 120 to get 255. So 255 plus the measure of angle H is equal to 360. Subtract 255 from 360, and we find out the measure of angle H is 105 degrees. What is the measure of angle L in the diagram below? We are given that angle J is 65 degrees, angle K is 95 degrees, and angle M is 33 degrees. We don't know what angle L is. That's the one we're trying to find right here. But we do know from the quadrilateral interior angle sum theorem that they have to total 360 degrees. Here's angle L, and they have to total 360. If I combined 65, 95, and 33, that's equal to 193, plus the measure of angle L is going to equal 360 degrees. Subtracting 193 from both sides, we find out that the measure of angle L is 167 degrees.